So, today we're going to dive into this really fascinating research paper that sits right at the intersection of artificial intelligence and healthcare, and it tackles a huge problem. How can we make medical diagnoses both incredibly accurate and, well, radically more affordable? The paper proposes a pretty wild solution, and it all starts with a single, kind of surprising number.
Yeah, $591. That's what it can cost for just one patient to get a full panel of lab tests to predict mortality from sepsis. Now multiply that by thousands and thousands of patients, and the costs just become astronomical. But what if? What if we could get the same or maybe even better results for just a fraction of that cost?
You see, this high cost puts doctors in this constant bind. It's a real dilemma. Do they order every possible test just to be absolutely thorough, racking up massive bills for the patient and the whole healthcare system? Or do they try to be cost-conscious, order only a few tests, and risk missing that one crucial piece of the puzzle that could save a life? It's a high-stakes trade-off they have to deal with every single day.
And this is exactly where the research comes in. It proposes a third option, an intelligent assistant for doctors. What if you had an AI that could learn the most efficient path to a diagnosis, perfectly balancing that need for information with the cold, hard reality of cost?
The approach they used is something called reinforcement learning. And honestly, the easiest way to wrap your head around it is to think of it like a game. The AI is the player, and its goal is to win. In this game, a move is just ordering a panel of lab tests. So the AI makes a move, it gets new information, and then it decides its next move. And a win? Well, that means achieving a confident, accurate diagnosis while spending as little money as possible. This slide shows us exactly how that game is played. The AI starts out with just some basic patient info. Its first move? Order a specific test. It gets the results back, and that moves it to a new state where it has more information. From there, it makes its next move, and then the next, until it has enough data to make a really confident diagnosis. It's learning this dynamic, step-by-step strategy, just like a human doctor does, but one that's perfectly optimized for cost and accuracy.
Now, in the world of computer science, this game actually has a formal name, a Markov decision process, or MDP for short. It's the perfect mathematical language for this problem because it's designed to model exactly this kind of thing, sequential decision-making, where an agent learns the best actions to take to maximize some kind of long-term reward. So the game our AI is playing is very, very real.
Okay, so the framework is in place. But, and this is a big but, this is where the researchers hit a major wall. See, you can't just tell the AI to be accurate. In medicine, the very definition of accuracy is way more nuanced, and that creates this really difficult puzzle for standard AI methods.
The problem really starts with the data itself. For a lot of diseases, the vast majority of patients in a dataset are actually healthy. You might have only 5%, maybe even fewer, who are actually sick. This is what's known as imbalanced data, and man, it can seriously mislead an AI.
So here's the crucial point. If a disease is only in 5% of patients, an AI could achieve 95% accuracy by doing something totally useless, just guessing that every single patient is healthy. I mean, how useless is that? That's why clinicians don't rely on simple accuracy. They use a metric called the F1 score, which cleverly balances both kinds of errors, false positives and false negatives. It's a much more reliable measure of how a model is actually performing.
And that brings us right to the core puzzle. The F1 score is what matters, it's what doctors trust. But how on earth do you get a reinforcement learning agent, which is used to getting simple little rewards, to optimize for a complex goal like this?
So this is the technical heart of the problem. Standard RL works by just adding up simple rewards over time. Plus 1 point for this, minus 1 for that. But the F1 scores formula is what's called nonlinear. And in simple terms, that just means you can't add up rewards for each correct guess to get the final score. The score depends on the total count of true positives, and false negatives all at once. This complexity just completely breaks that simple step-by-step reward system that standard reinforcement learning relies on.
So, faced with this puzzle that seems totally unsolvable, the researchers developed this incredibly elegant mathematical breakthrough. They found a way to reshape the entire problem, turning the impossible into something solvable.
And they did it in 3 brilliant steps. First, they just reformulated the goal. They focused on maximizing true positives and true negatives, because they knew that would always increase the F1 score. Second, they looked at the problem from a totally new angle, using a different mathematical language. And third, and this is the really clever part, they used a mathematical trick to essentially flip the problem upside down, which turned it into something much easier to handle.
And this quote from the paper just perfectly illustrates the result.
After this whole mathematical transformation, they had this aha moment. As they write, the problem was now finally a standard cumulative sum MDP problem. The unsolvable puzzle had become a textbook case that standard reinforcement learning could handle perfectly.
This whole technique is called reward shaping. You can think of it as the art of taking a really complex, real-world objective like the F1 score and translating it into a simple set of instructions an AI can actually follow. So now, the AI gets a specific reward for a correct positive diagnosis, another for a correct negative one, and a specific penalty for the cost of each test. With these simple rewards, it can finally learn that optimal strategy.
Okay, so the theory is super elegant, but does it actually work in the real world? Well, the researchers put their AI to the test on 3 real-world clinical datasets, and the results, wow, they were just stunning.
Let's just start with the headline number. 85%. Across their experiments, their AI was able to get diagnostic accuracy that was as good or even better than the best methods out there, but with up to an 85% reduction in cost. That's not a small tweak. That is a monumental leap in efficiency.
Let's go back to that sepsis data for a second. The baseline model, which is a really powerful algorithm, needed that full $591 panel of tests to get an F1 score of 0.500. Now look at their AI. Using its dynamic strategy, it not only beat that score, getting a higher F1 of 0.562, but it did so for just $90. Higher accuracy for about a sixth of the cost. It's incredible.
And check out the graphs here. All those red dots are possible testing strategies the AI found. But the real magic is that yellow curve that traces the very top edge of those dots. That's called the Pareto front. Just think of it as the line of perfect efficiency. You can pick any budget you want on the bottom, go up to that yellow line, and that's the absolute best accuracy you can possibly get for that amount of money. Their method doesn't just find one good strategy, it finds the entire frontier of optimal strategies.
And this is why it's such a game changer for doctors in the real world. The Pareto front is basically a menu of optimal choices. A doctor could say, okay, my patient's insurance only covers $100 of testing. They can look at the menu, find the $100 mark, and know exactly which sequence of tests will give them the best possible diagnostic power for that specific budget. It's flexible, it's powerful, and it's incredibly practical.
So what does all of this mean for the future of medicine? I mean, the implications of this work are just profound. It's moving us towards a smarter, more equitable healthcare system.
So let's just recap the big takeaways. This AI gets top-tier accuracy for a fraction of the cost. It completely replaces the one-size-fits-all, order-everything approach with a personalized strategy for every single patient. It gives doctors that full menu of optimal choices. And, incredibly, the AI can keep learning on the fly, constantly improving its strategy as it sees new patients. This is really a blueprint for a future of more personalized and accessible medicine.
So, I'll leave you with this final thought. We often think of medical care as this trade-off, right? Quality versus cost. But this research just flips that idea completely on its head. It asks a new question. What if your next diagnosis wasn't just world-class in its accuracy, but was also perfectly, intelligently, and optimally tailored to what you and the system can actually afford? That's the future this work is building.